All right, today we're jumping into the KMMR project. And let's be clear from the get-go. This isn't science fiction. This is not about getting energy from nothing. It's a serious, real-world engineering effort to build an entirely new kind of quantum engine. So let's break down exactly how they're trying to do it.
To really get your head around what the KHMR team is aiming for, just start with this question. Seriously, what if you could capture a single pure frequency of light, a perfect, unwavering wave, and make that the very heart of a machine? That's the core idea, and we're about to unpack it.
So what is this thing? Well, the KHMR is a whole new class of quantum device. And again, it's not about creating energy out of thin air. It's about converting energy from one form to another, but with a level of precision and efficiency that's just on another level.
And this number, this is the heartbeat of the entire system, 114.11 terahertz. This specific frequency in the mid-infrared range wasn't just picked at random. It is a very carefully chosen harmonic target. The entire reactor, from the materials they use to its physical shape, is engineered to resonate perfectly with this one single frequency.
So that's the official description. A quantum harmonic reactor basically takes an energy, say from a laser, and transforms it into this perfectly stable, pure beam of light at that target frequency we just talked about. A really good way to think about it is like a quantum gearbox for light. It takes a high-frequency input and it down-converts it into an incredibly pristine, powerful, and useful output.
Okay, so if your entire engine is built around a perfect wave of light, then your first and maybe your most critical challenge is, how do you build a perfect trap for it? And this is where the engineering gets really, really interesting.
And that question right there leads us to one of the most fundamental concepts in quantum engineering, the optical cavity. But not just any old box will do. You need one that has an exceptionally high quality factor, or what they call a Q factor.
This analogy just nails it. A low Q cavity, it's like a muffled bell. You hit it, and the sound is dull and dies out almost instantly. The energy just leaks right out. But a high Q cavity, that's like a perfectly cut crystal bell. You strike it, and the note is incredibly pure, sharp, and it just rings and rings for a long, long time. That's exactly what the KHMR needs to do, but with light. Their target Q factor of over 100,000, that means they're aiming to store that light energy with just breathtaking efficiency.
All right, let's get into the nitty-gritty of the hardware. We're looking at how the reactor's core is actually built. It's basically a microscopic pillar, a vertical Fabry-Pérot microcavity. It's an absolute feat of nanotechnology, and we can break the process down into 4 key steps.
So here's the recipe. First, you've got to find the absolute perfect crystal material. Then, you have to build mirrors that can actually trap the light. After that, you have to tune the entire system into a tricky state called double resonance, and we'll get to what that is in a second. And finally, you have to put it all together with almost unbelievable precision.
Choosing the material is absolutely critical. Now that first metric, nonlinear efficiency, that's basically how good the material is at doing that gearbox job of changing the light's frequency. And as you can see, orientation-patterned gallium arsenide, or OP-GaAs, just blows the competition away. It's more than 3 times stronger, and its thermal handling is an order of magnitude better, which is a huge deal when you're trying to trap high-intensity light.
So this is how you build a trap for light. The mirrors aren't made of silver like you'd think. They're actually photonic crystals. We're talking about dozens of alternating layers of semiconductor material, and each and every layer is engineered to be exactly a quarter of a wavelength of that target light. It's mind-bogglingly small. And the combined effect creates a mirror with over 99.99% reflectivity. The light is just stuck in there, with almost no way out.
And just when you thought it couldn't get any harder, here's where the engineering challenge gets really intense. The cavity doesn't just need to trap the target 114 terahertz frequency. It also has to trap the input pump frequency at the exact same time. Think about it like this. Tuning a cavity is like getting a guitar string to ring at one perfect note. Now imagine trying to build that one string so it perfectly rings with 2 different notes simultaneously. Getting a single cavity to do that is a massive, massive achievement. It's what makes this whole design so revolutionary.
So, you've got the blueprint. You know how to build it, in theory. The next step was to actually build it and prove it works. And for that, the project moved into a highly controlled lab, a decommissioned scientific chamber at the Bulgarian Academy of Sciences.
The goals for this initial proof-of-mode phase were crystal clear. It was a simple checklist. First, build the prototype. Then, prove it can actually trap that target frequency.
Show that the energy conversion really works. Measure how good the trap is, that's the Q factor. And finally, generate that first stable, coherent beam of light. This quote from the project's own documentation really zeroes in on the single most important goal. Before anything else, they had to prove that their nano-engineered trap could hold on to that very specific frequency of light and do it stably. Everything else, all the incredible applications we're going to talk about, it all flows from that one fundamental success. And to get that verification, the experimental conditions had to be, well, extreme. We are talking about an ultra-high vacuum cleaner than deep space, just to make sure not a single stray molecule could mess things up. The alignment of the parts is controlled with the precision of 1/10 of a nanometer. That is smaller than a single atom. And the temperature is kept stable to within fractions of a degree. This is not a tabletop experiment. This is high-precision quantum validation at its most demanding.
So, they've designed it, they've built it, and they've tested it under these insane conditions. But what's the point? Why go through all this trouble just to create a perfect beam of 114 terahertz light? Well, this is where we get to the real-world impact.
A stable, high-power source like this could be a total game changer. Imagine next-generation microchips manufactured with the precision we can't even achieve today, etched by pure light. Or what about transporting energy not through wires, but as a focused beam for industrial processes? For defense, this opens up completely new possibilities for secure communications that are literally impossible to intercept. And for science, it's a fundamental new tool, a building block for exploring the quantum world in ways we've only dreamed of.
When it comes down to it, the KMHR project is about more than just one device. It's a test case for a whole new approach, engineering quantum effects with industrial-level precision. And that leaves us with a pretty big question. If they succeed, are we looking at the blueprint for an entirely new era of quantum engineering?